I'm going to teach you today how to write an electron configuration of an atom. In an atom, electrons and the nucleus interact to make the most stable arrangement possible. The way in which electrons are distributed in the different orbitals around the nucleus of an atom is called the electron configuration. In the quantum mechanical model, electrons occupy energy levels. If you'll take a look at the periodic table of elements, we have 7 energy levels. Energy levels have sublevels S, P, D, F. Sublevels have orbitals. S has 1, P has 3, D has 5, F has 7. If we want to know how are the electrons arranged in an atom, we will write its electron configuration using the concepts of quantum mechanical model. Electrons fill the orbitals according to a pattern. Using the information in the table, we can rewrite it this way to find the pattern. Remember, numbers 1 to 7 are the energy levels. S, P, D, F are the sublevels. We will draw arrows starting with the 1s orbital. So we'll have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, and so on. Considering the number of orbitals per sublevel, S can hold a maximum number of 2 electrons, 6 for P, 10 for D, and 14 electrons for F. Therefore, we'll have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, 7p6, and so on. In writing an atom's electron configuration, 3 rules are considered: the Aufbau principle, the Pauli exclusion principle, and the Hans rule. The Aufbau principle states that the lowest energy orbital is filled first. For example, the 1s orbital is filled first before the 2s orbital is occupied. In this way, the electrons of an atom form the most stable electron configuration possible. The Pauli exclusion principle states that a maximum of 2 electrons may occupy a single atomic orbital, but only if they have opposite spins. An electron spins in either clockwise or counterclockwise direction. Hans' rule states that a single electron with the same spin must occupy each orbital in a sublevel before they pair up with an electron with an opposite spin. For better understanding of these rules, let's have some examples. Let's write the electron configuration of boron. In the periodic table of elements, boron has an atomic number of 5, meaning it has 5 electrons. So following the pattern, boron's electron configuration is 1s2, 2s2, 2p1. Since we started filling the lowest energy level, we satisfied the Aufbau principle. When you add the exponents 2, 2, 1, the sum is equal to the number of electrons of boron. Orbital notation is another way of writing electron configuration to provide more specific information about the electrons in an atom of an element. In doing orbital notation, fill each orbital with arrows following the Pauli exclusion principle and Hans rule. This is the orbital notation for boron. We'll have 1s2, 2s2, 2p1. Now, let's try writing the electron configuration of sodium. Sodium has an atomic number of 11, thus it has 11 electrons. Its electron configuration is 1s2, 2s2, 2p6, 3s1. For its orbital notation, we'll have 1s2, 2s2. Look closely how the filling of 2p orbital followed Hahn rule. Each electron with the same spin occupied each orbital first before they paired up with another electron with an opposite spin. And 3s1. How about the electron configuration of chlorine? Chlorine has 17 electrons. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Its orbital notation 1s2, 2s2, 2p6, 3s2, and 3p5. I hope you enjoyed the lesson today. Thank you!